We want to compute the following indefinite integral. We think here of applying the integration by parts, and the challenge is to know what function we have to differentiate and what function we have to integrate. So since here we have ln x multiplied by a function that is easily integrable, we can choose to differentiate ln x and to integrate x over square root of x squared minus 1. So let's take u equals ln x, and hence du is 1 over x times dx, and dv equals x over square root of x squared minus 1 dx. Now we can see that x over square root of x squared minus 1 dx is of the form f prime of x over 2 times square root of f of x, where f of x is x squared minus 1. So an antiderivative of this function would be square root of f of x, which means that v is square root of x squared minus 1. Now the integration by parts formula gives us... So now we have to deal with this integral, so let's call it j. So I'm going to give two different approaches to deal with this integral. The first approach is the substitution t equals g of x equals square root of x squared minus 1. Now, as we can see here, this substitution means that dx over x is t over t squared plus 1 times dt, which means that our integral j becomes the integral of square root of x squared minus 1. So this becomes t times dx over x, which is t over t squared plus 1 dt. So we have here a rational function to integrate, and the first step is the long division of t squared by t squared plus 1, which gives... Now we express the answer in terms of our variable x. So we have j equals square root of x squared minus 1 minus tan inverse of square root of x squared minus 1 plus c. And the final answer for the integral I is... The second approach to compute the integral j is by inverse trigonometric substitution, since we are seeing a function in the integrand of the form square root of x squared minus a squared, where a is equal to 1. So we set x equals a secant theta, so here secant theta, with theta between 0 and pi over 2, so that the secant function is 1 to 1. So in this case, we know that dx is sine theta times secant square theta d theta. And with this substitution, the integral j becomes, where we use the trigonometric identity secant square theta minus 1 equals tan square theta, and then square root of tan square theta is tan theta, because tan theta is positive since theta is between 0 and pi over 2, so in the first quadrant. So using the trigonometric identity sine square theta equals 1 minus cosine square theta, our integral j becomes the integral of 1 over cosine square theta minus 1 d theta, which is tan theta minus theta plus c. Now to express our answer in terms of the variable x, we remember that theta is secant inverse of x. Finally, using a right angled triangle showing a real number theta whose secant is equal to x, we deduce that tangent theta is square root of x minus 1. So j becomes, and therefore the final answer for the integral I is I equals square root of x squared minus 1 times ln x minus j, so minus square root of x squared minus 1 plus secant inverse of x plus a constant c. Now if we compare this answer to the previous one, we see that we have secant inverse of x instead of tan inverse of square root of x squared minus 1. Now, since these two functions are antiderivatives of the same function on a given interval, we deduce that the difference between these two functions is a constant. And actually, we can prove that on the interval 1 infinity, which is the range of secant theta when theta is between 0 and pi over 2, we have secant inverse of x is equal exactly to tan inverse of square root of x squared minus 1. So this is why actually both answers make sense.